Hello and welcome to this educational video on Bragg's law. Today, we'll explore how this fundamental principle helps in understanding the interaction of X-rays with crystal lattice and its importance in material characterization. Bragg's law is a special case of law of diffraction. It determines the angles at which X-rays are constructively scattered by a crystal lattice. The relationship is expressed as n equals to d sine theta, where n is the order of reflection, lambda the wavelength of the X-rays, d the interplanar spacing, and theta the diffraction angle. When X-rays hit a crystal, they are either transmitted or scattered. Constructive interference occurs when the scattered rays from two parallel planes are in phase. This phenomenon creates a diffraction pattern, which can be analyzed to understand the crystal structure. The incident angle theta impacts the diffraction pattern, dictating whether constructive interference occurs. The angle to theta between the transmitted and diffracted beam is measurable in experiments. Bragg's law is crucial for material characterization, helping us analyze the structure of crystalline materials. It's used to determine atomic spacing by measuring diffraction angles. In X-ray diffraction (XRD), it reveals details about crystal structure, phases, and lattice distortions. It also helps determine grain sizes, where broader XRD peaks suggest smaller grains, quantified by the Scherer equation. Bragg's law also reveals lattice distortions, important for designing materials with specific properties, like strength or thermal stability. In short, Bragg's law bridges atomic-level details with real-world material applications. For the analysis, start by measuring the diffraction angle theta from the pattern. Using the known wavelength lambda, calculate the interplanar spacing, d with the formula n lambda equals to sin theta. Next, examine the peak positions, intensities, and widths. Compare these with a database like ICDD to identify the crystal phase and determine the unit cell parameters. Lastly, broader peaks often indicate smaller grain sizes or lattice distortions, providing critical insights into the material's structure and properties. This simple calculation demonstrates the power of Bragg's law in deriving essential material properties. The results of Bragg's law depend on several important factors. First, the wavelength matters. Shorter wavelengths, like X-rays, provide higher resolution, making them ideal for analyzing fine details in small crystals. Next is the interplanar spacing. Larger spacings result in smaller diffraction angles, while smaller spacings produce higher angles. Finally, the crystal structure affects the outcome. Different symmetries produce unique diffraction patterns and determine the intensity and position of the peaks. These factors collectively influence the accuracy and clarity of Bragg's law results. And these are the references. Thanks for watching.